Hi everyone, my name is Manav and this is the first video on my channel. So basically I'm a Go backend engineer and in this video we are going to learn about hashing. And it is a very interesting topic, but before we even begin talking about it, we need to understand why do we actually need it or how did it even arise at the first place. So to understand that, we need to understand a simple problem which is called the search problem. So basically, we have a list of elements. Now it could be sorted or unsorted. So we call a list of elements sorted if all the elements are in increasing order, and we call it unsorted otherwise. So let's say we have a list of elements and it could be sorted or unsorted, and we want to find a specific element. So in our case, let's say I want to find the element 8. Now there are a couple of ways to do that. The first one and the most basic one that that all of us know or have read about it in our coding journey is linear search. So what actually is linear search? So basically we just go at each element one by one. So we are traversing the list one by one, each element, and we check, hey, are you 8? And it says no, I'm 3. And then I ask this, are you 8? And it says no, I'm 6. And so on and so on and so on, and we actually get to the point where 8 is stored and we access it. So this is called linear search, and we need to talk a little bit about it. So the thing is that linear search, the good thing about it is it works with sorted as well as unsorted arrays. So it is a pro point about it. But the thing that we don't like about linear search is that its time complexity is O of n. Now, don't worry if you don't know what time complexity is. So I'll explain. So what I'm saying is that let's say we are doing a linear search on a list of 1 million elements. So n is just the size of the list. So n here would be 1 million. And let's say the element that we want to find is at the last index. So it would be at the 1 millionth index. So what we would do is we would go on to each element one by one. We check if it is the element that we want to find, and in worst case, where the element that we want to find is at the last index, we'll go through a million elements. That is why we say that its time complexity is O of n. So we'd be traversing a lot of elements. Now, this is a good approach, like linear search is good, but we wanted to make it faster. So what we want is that if you're searching something, we don't actually want to search the entire array. It is quite slow. So the next thing that engineers came up with was binary search. Now, this is also something that a lot of you who have done DSA would know about. So the thing about binary search is it says that I won't actually search all of the elements. I'll continuously divide the search space. So what it says is, first of all, unlike linear search, binary search says that in my list, all elements should be sorted. And now the thought comes, why actually do we want the elements to be sorted? So let's do a example and you'll understand. So let's say I want to find 8 now. So what binary search would do is that it won't go on searching from the beginning to the end. It'll just go to the middle of the entire list, and it will ask this element. The middle of this list is 5. It will ask, hey 5, are you 8? And 5 says no. So now what binary search does is it asks, okay 5, is it bigger than you or is it smaller than you? And 5 says obviously it is bigger than me. And since the array or the list is sorted, we know that it cannot be on the left. So 8 cannot be on the left. So we just delete this entire part. You see how fast the search became? So now the array just consists of these two elements. And we again take the half or the middle, and sometimes it could be 6 or 8. And let's say it is 6 in this case. So now the binary search asks, hey 6, are you 8? It says no. So it says okay, so 8 is bigger than you, so I'll cancel everything on the left. I'll cancel everything on the left and I'll just focus on the right part. So what actually are we doing? At each iteration, instead of searching each element one by one from left to right, we are actually dividing the entire array in half, and then again in half, then again in half. So the time complexity that comes is O of log n. Now Just to revise, linear search works with sorted as well as unsorted, but its time complexity is O of n, which is quite slow. But if the array is sorted, then what we can do is we can use binary search and we get a time complexity of O of log n. So just to make you feel how fast this is, let's say I have an array of 100 elements, then in linear search I'm making 100 comparisons. But in binary search, I'm just making 7 comparisons. Can you see how fast this became? And it becomes even faster as the number grows up. So it is great, right? We have a logarithmic of n approach. So why do we actually need hashing? We need hashing because we want it to be instant. So I'm saying no matter if I have 100 elements, no matter if I have 1,000 elements, maybe I have a million elements, but I want an instantaneous O of 1, which is called a constant time complexity approach. So whenever I give the element, I want it instantly from my list or wherever it is stored. So before we move on to hashing, we actually have a shortcut and it is called a direct address table. So let's talk about it a little bit. So what direct address table does is it says, let's say I have a list of elements. What I can do is I can actually store them at the index of their values. So what I'm saying is, let's say I have 2 here. So what I would do is I will store 2 at the index 2. Then I will store 3 at the index 3. And so on. I'll store 5 at index 5. Then I'll store 6 at index 6 and I'll store 8 at index 8. And you would think that, okay, now let's say I want to find 8. What I would do is I would just go to the list at the index 8 and I would find it. And I'd be like, hey, that's amazing. We wanted O of 1 approach. Like we wanted an instantaneous approach and we found it. So that's great. Why do we need hashing for? So there are a couple of bad things about this approach. So first of all, we cannot support strings. So here the list contains integers. So it is great. We can store it in index forms. But what if the list contains strings? So let's say the list contains names or etc. which are strings. So in that case, direct address table completely fails. Moreover, let's say the numbers that I have in list are actually IDs. And the thing about IDs is maybe my IDs are 8 digits long and I just have 2 IDs in my list. Let's say the first ID is 0000001 and the second ID is 999999990. So if we go about the direct address table approach, I would need a table, or you can say I would need a list of size a million and I would just be storing 2 elements in it. So do you see how much wastage of memory I'm doing? And in some cases maybe I wouldn't be able to make a list that big and I would be wasting so much of space. So now to solve all of this, we come to hashing. And now we have finally arrived to the interesting part. And let's begin with hashing. So here's a little bit of theory. I'll read it out and then I'll explain it. So don't get scared if you find this, intimidating. So it says we want the O of 1 speed of direct address table, but we don't want to spend GBs of memory. Instead, let's create a reasonable sized array of size m and find a smart way to map any key into an index between 0 and m minus 1. So what it is saying is we want a 0 of 1 lookup speed. So what does 0 of 1 means? It means that if I give it element, it should tell me exactly, like it should tell me instantly where exactly is it stored. And it says I don't want to do it using direct address table approach, which would take a lot of memory. I want to do it in a smarter way. So what actually are we doing is we are taking a table. So I'll just copy this below. So this is not a direct address table. So we'll just take a table which is just a simple list of size m. So here, can you tell me what the size of this list is? You're right. The size of this list is 10. So I'm saying let's create a reasonable sized array of size m. So here the size of the list is 10. Okay, I'm making a lot of typo errors today. So m is equals to 10 here, and we have to find a smart way to map any key into an index between 0 and m minus 1. So we have the index 0 and m minus 1, which is 9. So basically this whole sentence is just saying let's find a smart way to transform these big keys into a small range of size 0 to m minus 1. So let's see how it is actually doing that. So what we want is that we would have a key, then we want to run a hash function, and that hash function would give me the index between 0 and m minus 1. So ideally, if I pass in this number, let's say this big key, I'll make it pass through the hash function and it would give me an index. Let's say it would give me the index 5 and I will store it at 5. So do you understand what hashing is trying to do? It is trying to compensate for the errors, or you can say for the drawbacks of direct address table, and it is trying to give us a better approach to storing data and finding it instantaneously. So let's see what are the components of hashing. So I just told you that we'll use a hash function, but it won't come out of thin air, right? So let's see what the components of a hash function are. Now a hash function just has two small and simple components. Now don't get afraid with these big diagrams or stuff. It is very simple. So I told you that that we have a key, we pass it through a hash function and we get an index which is in the range of the list that we have. Now the hash function has just two small parts. It has a hash code generator and a compression function, and they serve two very key functions. So the first thing is the hash code generator. So the sole job of hash code generator is to take the key, which could be a really big number, it could be a negative number, it could be a string even. I told you about strings right here, that maybe we can have strings as the elements in the list. So the hash code generator takes anything that we give it and it converts it into a massive number. Now this number could be positive or negative, but it is a really big number. And the sole job of hash code generator is to take the input and generate a very unique, output for it. So unique in the sense that every time I give it a key, let's say every time I give it 8, it should generate the same number. It should not be like if I give it 8, it's generating 5 at this moment, and then again I put 8 in it and it's generating 6. So we'll talk about it in a while. So the job of hash code generator is to take the key and to generate a big number from that key. Then we have the compression function. So if we take this massive number, we can just store it in the list that we have, right? That's the whole problem that we were facing with direct address table, right? So what we do is we take this massive number and we give it to the compression function. And this compression function, it compresses that number, that really big number, into our range. What is our range here? The range is between 0 and m minus 1, which is the size of the list. I think this is something that you all must have known, right? That in then like whenever we have an array, we have like sequential numbering of the elements in that array, which is called indexes. So what we want from the compression function is take this big number and compress it into a single number. So we get the index and then we can store it. Now I know a lot of doubts came into your mind, right? So some of the doubts would be, hey, can you give a dry run, which I will give you. Then another would be, okay, how many types of hash code generators or compression functions are there? And then another doubt would be, like you said that uh, I pass in 8 and the hash code generator or the compression function gives me an index 4, and if I pass in 12 it also might give me 4. So what if at the same index I get two elements, which is inevitable if I have just a storage of size 10, and if I have 20 elements, then obviously at some point the same storage would have multiple elements. So this is called collision, and I don't want you to worry about this right now. This is a topic of next video. But what we would see is like a dummy flow of how actually a hash function looks like. In the next video, we'll also see all the types of hash function that exists. But in this video, we are just going to see a dummy flow. And also we're going to see what actually are good properties of a good hash function. So what actually are the properties of a good hash function? So let's start with the dummy flow. So let's say I have a key, and let's say the key is I'll do it here. Let's say the key is apple. So what will happen is I will pass it to a hash code generator. Now hash code generator will create a massive number out of it. So you might ask, okay, tell me how will it generate a number? And I'll say this is the topic of the exactly next video that you're going to watch once this video completes. So let's say the hash code number, the hash code generator gave me a number called 487634. Now it will go through the compression function. Now in our case, we have just 10 elements in the array, like 10 storage spaces in the array. So I'd say the compression function that I'm using is modulo of 10. So what is modulo of 10? It's simple. Modulo means I'll divide this big number from this number at the right side, and whatever the remainder is would be my output. So it will say, okay, the compression function is modulo of 10. So it would give me 4, right? And this is the index that we want. So this number, I'm sorry. So this number, this thing apple would be stored at index 4. So if I had to write it down, I'll say apple here, right? So I think you have a slight bit of idea. I know you're confused, like, hey Manav, how did apple turn into this number? And how did you decide that you're going to use modulo of 10 as compression function? And this is exactly the topic of our next video, where we'll talk about hash functions and all the types that are there. So just wait a while for that. But I give you a rough flow of how things happen. Now the last thing before we leave this video is, what are the properties of a good hash function? So there are just 3 properties that we look for when we are making a hash function. The first one is determinism. So this is a tricky topic. So like, listen to me carefully. So it says that whenever I pass a key, so let's say I pass apple, no matter how many times I use the hash function to generate a key for apple, every time it should give me the same index, or let's say key. So I'm saying, let's say I pass an apple 10 times, then all of those 10 times the hash function should give me 4. That is called determinism. But don't get confused by this. So if I pass in, like, let's say if I pass an apple 10 times and it gives me 4, and then I pass an orange 10 times and it also gives me 4, then it is completely fine. It is following determinism. So what is happening here is collision, and I told you that is the topic of the video in later in this series. But if I pass in apple once and it gives me 4, and then I pass in apple, it gives me 4, and then I pass in apple again and it gives me anything, let's say 9, then this is wrong. This is not allowed. So you have to understand, determinism means that every time I pass in the same key, I get the same index. The next thing is low computation cost, and this is easy one. So the entire thing that we want hashing for is that we already had a logarithmic of n solution. So we wanted something faster, which was instant lookup. So if the computation is doing, like, if we are doing some intense mathematical computation to generate the indexes, then the entire point of using hashing is lost. So the hash function should have very low computation cost. And the last thing is uniform distribution. It is also very easy. It says that, let's say I pass an apple, orange, so and so and so, and every time it generates 4. So what would happen is all of those fruits would start piling in on this index, and all of the index would be empty. Or maybe it passes, or it generates indexes for just 2 elements. So it says, okay, I pass an apple, it gives me 4, then I pass an orange, it gives me 6, then I pass in mango, it gives me 4 again, and so on and so on and so on and so on. So it is not uniform distribution. So uniform distribution means all of those keys that we have here, all of these indices that we have there, that we have here, should have uniform load. So they should have uniform number of elements that they are storing. So that is called uniform distribution. So that is it about hashing. So that is it about hashing. In the next video, we are going to look at all the types of hash function that are available. And in the next video to that, we are going to look at collisions and how to solve those. So yeah, this is going to be a really interesting playlist, and stay tuned. I'll see you. Bye bye.